Hello, students. Today I would like to continue our discussion of the Gauss-Jordan elimination process, but now introduce the topic of a reduced matrix. What we did in our last lecture covered the process of Gaussian elimination, but now what we want to do is define a particular type of matrix that will make the process possibly a little bit easier and let us know when the solution will be apparent to us. So let me share the screen and say something about the reduced matrix. Now, this is what you have in your lecture notes, and I wanted to take the opportunity just to go through the basic definition. And I think this actually characterizes the reduced matrix in a way that's very straightforward. Now, when you use the concept of reduced matrix, you will always see the following description: reduced row echelon matrix, or RREF. That happens to be an acronym that many students use when they are basically working towards the reduced matrix form. And the echelon has to do with the shape of the reduced matrix. I'll say more about that. But what does the reduced matrix have as far as characteristics? Well, the very first one is easy, but it isn't always apparent. Rows containing all zeros are below any row containing a non-zero entry. So we remember when we were able to achieve a row of zeros in the Gauss-Jordan elimination, that would imply that we had a free variable. Now, of course, if there is no free variable, you don't have the row of zeros. So again, this is a special case that can happen, but certainly not always. The second one, or the second characteristic, is the leftmost non-zero entry is a 1. And notice here I've called it a leading 1. When we think of all of the entries to the left of the vertical line, remember the vertical line denotes the equal signs in our systems of equations. And so that's not required, but the ones that we achieve will actually stand for basic variables like x1, x2, etc. Of course, if we had a 1 in the right-hand side, that would not have the same impact. But what we want to do in a reduced matrix, if we have a non-zero entry in a row, the leftmost entry will always be a 1. Now, one thing about the leading 1 that is very important when we consider the entries to the left of the vertical line is that we want all of the other entries in the column containing the leading 1 to be 0. So we want that column to be unitary. That is, we have the leading 1 and any other entries in the row will be 0. Now we realize that one of the Gauss-Jordan elimination row techniques, that is an elementary row operation that allows us to create a 0, is when we multiply a particular row by a constant and add it to another. That's creating the zeros. We like the zeros. So again, that process is simplifying the matrix so we can read the solution. So when we have the unitary columns, that's exactly what we were doing in the previous set of problems when we had not actually defined the reduced matrix. And then the last one, which is actually very important, is that we want the leading ones to form a staircase. That is, if you have a subsequent row with a leading 1, you would like the leading 1 in the rows above to be again to the left of that, or as you go down through the matrix, you want the leading ones to be to the right. So that creates a staircase pattern. Now, The first time you think about these characteristics, they seem a little bit difficult, but if you go back and you look at the problems that we have done in the previous section with the two equations, two unknowns, you'll start to notice this. It's just a little bit more apparent in the larger matrices. So I just want to cover a couple of examples from your worksheets so you can actually see what a reduced matrix looks like. So when we have a situation like number one, notice this is a system of three equations in three unknowns. So this is a larger augmented matrix. But what we want to notice here is that we don't have the staircase pattern. That is, we would like, if we've got upper rows, that the leading one be to the left. Okay, we always want that. And so when we think about correcting that, we would say, since this one is actually to the left as a leading one, we can interchange the first and the second row using the notation here, which is an elementary operation. And then we see now that we have the staircase pattern. That is, all of these ones are leading ones, and we notice that the other entries in the column containing the leading ones, as we see here, are zeros. We have the staircase pattern, we have the unitary columns, we have the leftmost entry in the non-zero rows being a 1. Now, of course, we don't have to use the first characteristic here because we don't have a row of zeros. So just remember, when you think about what we did before, and I commented on this in lecture, is that when you have a situation like this, you indeed have a unique solution, because you could say for this particular matrix, x1 equals 8, x2 equals 2, and x3 equals 3 for a unique solution. So this should not be surprising to you. We see that if the goal is the reduced matrix, then we should be able to read the solution. And of course, we will also see when there is no solution. I mean, when we characterize the solution of a system, that includes the case that there could be no solution. So let's look at a couple more examples. Let's look at 4 and 5. Notice when we look at 4 here, we think about the existence of the leading ones. Now, another thing that students often worry about is that if you have the elementary operations to create zeros, then you do it. But if that operation is not available without destroying other zeros that you've already created, then that would not be something you would entertain. So what we can see here is that we notice we have a leading one and the unitary column here. And we also go over here and see that we have another unitary column. So this particular one could be classified as a leading one. But notice here, what we have is that it appears that this one is also a leading one, but we don't have a zero here. That is, we need a unitary column. We would need a zero in this particular entry, but we know that's possible to do if we simply multiply row 2 by -4 and add it to row 3. And when we do that, of course, the zeros don't change anything, but the -4 plus the 4 gives us the 0. And then, of course, the -4 times the 12 is a -48, plus 5 gives us a -43. And this is reduced. So again, always remark in lecture, if we can create more zeros, then that's what we do. Don't worry about following a specific set of elementary row operations. That can introduce fractions and awkward numbers maybe too soon. Work to create the zeros in the simplest possible patterns you can using very simple arithmetic if it is possible. And then you avoid some of the awkward fractions that can be very tedious. Now, if you look at number 5, that's kind of a freebie. I mean, it is clearly reduced because it looks exactly like this. So again, um, maybe the reduced matrix isn't always the way you have to look at solving a system. You're thinking you could stop and then back substitute like you did when you were dealing with all the coefficients and the variables. But because we do have the reduced form of the augmented matrix, or just a matrix in general, we certainly set ourselves up to be able to state the solution, and that's really quite important. Now, let's look at some examples where we have a larger matrix, or we have situations where we have for instance, maybe we have 3 equations and 2 unknowns in an overdetermined system. We'll think about that too. But one of the simplest ideas that you see from your lecture notes is to now, as we've looked in the reduced matrices, look at 3 equations and 3 unknowns. Now, what I've done here is just go through the elementary operations here. So we will go through this, but the main thing is that now when we actually start to do our work, the goal will be the reduced matrix. I'll say this, in order to get comfortable with the reduced matrix, we have to now let that be our goal. Now, of course, we start with the system and we form the augmented matrix. So we have the 1, -1, 1, 0. Then we have 2, 3, 5, 1. And then we have 3, 2, 4, 7. Now, like I said before, often we don't have the luxury of a leading 1 here. When you have that, then that's really a plus because we know it's easy to create zeros. Like I said before, sometimes we don't create the leading 1 because it introduces awkward fractions, but we can still create zeros because the arithmetic may align itself in such a way that it's very simple and straightforward. So you always can determine how you want to create the zeros. Like I said before, you are the navigator of the arithmetic. So don't be confined to a certain order of operations. Create the zeros, and then you can always go back and create the leading ones in an appropriate fashion that maybe, and in many cases, simplifies the arithmetic. So now we can go ahead and do that. Let me just go through these operations. By now you've become very good at this, but it's always good to practice. So of course, to make the 0 here, we need to multiply row 1 by -2. And to create the 0 here, we need to multiply row 1 by -3. So again, -2 row 1 plus row 2, and -3 row 1 plus row 3. And when we do that, we see we get our 2 zeros here. And then, of course, the other entries here we get by simply doing the arithmetic. Let's go through one of the rows just to verify that we indeed have that. So we'll look at this particular operation. So -3 plus 3 is 0. -3 times the -1 is a +3, plus 2 is equal to 5. And then we have -3 times 1 is a -3, plus 4 gives us a 1. And of course, the 0 here will not change the 7. So the same operation as before. But now what we see is we have a very good situation here that will give us the unitary column that we need for this leading 1. Now, as I've said before, notice it's real easy to create a 0 here. We don't necessarily have to convert this to a leading 1. That's what I was saying before. We can always do that later. But now, of course, if we just multiply row 2 by -1 and add it to row 3, that will create the 0 that we need here. So instead of getting the leading 1 first, let's go ahead and create a simple 0. So when we do that, notice we easily get the 0 where we need it. And then, of course, we have -3 plus 1 is a -2, and -1 plus 7 is a 6. So now notice this is on the route to a unique situation. Now, when we look at this, we're thinking, well, we'll just go ahead and get the leading one. The 6 is divisible by the -2, so that's very simple arithmetic. We'll go ahead and create that, and that'll help us make zeros above that 1. So of course here we just multiply row 3 by -1/2, or the reciprocal of -2, and that gives us the 1 here, and of course the 6 times the -1/2 is a -3. So we still haven't created the 1 here. We don't need to, we'll do it eventually. But now we see, in order to make this a reduced matrix, we need to create a 0 here and a 0 here. So now, of course, if we multiply row 1 by -3, add it to row 2, we get the 0 where we need it. And then, of course, -1 times row 3 plus row 1 will give us the 0 here. And so now, when we create those two zeros, we're thinking we're pretty much done. Now, at this point, when we did the arithmetic for row 2, notice we introduced a 10 here. And so you're thinking, okay, well, that's some simple arithmetic. We can go ahead and create the leading one for row 2. Again, there is nothing about the operations that is unique. The guiding principle is this: create as many zeros as you can, but do not undo zeros in the process of trying to create a 0. If that starts to happen, then that's where you have to stand back and say, let me analyze the matrix a little more carefully, because you don't want to undo something that is needed for the reduced matrix form. So again, let that be the guiding principle. So now, of course, we'll get our leading 1 by multiplying row 2 by the constant 1/5, and that gives us the 1 here and the 2 here. So you're thinking this is basically reduced except for the last entry here. Notice, and this is why this method is far superior to the methods of dragging all of the variables along. This codifies the process of solving linear systems in such a way that it's very mechanical. However, it provides the person doing the process much leverage, that is, much flexibility, to create a system of arithmetic that is straightforward and as easy as possible. So now we're pretty much done. We can see, we can just basically add row 2 and row 3, since these are additive inverses, to get the 0 here. So now we've got the 1, the 0, and the 0, and of course 2 plus 3 is 5. And now the nicest reduced matrix we can imagine. We have 3 unitary columns. We have the staircase pattern, the leftmost entries in all the non-zero rows, which is all we have, are 1s. Of course, there's no row of zeros, and we are done. And so the simplest and the most effective way that we find in basically obtaining the reduced matrix is that in the unique case, we have a very, very clear situation. Now you're thinking, if you have some rows collapse into zeros, then that's probably going to be a little less work. However, you do have to navigate the idea of a parameter or free variable. But when you're working towards a unique solution, then you can pretty much depend on having a fair number of operations. Again, someone else can do the same problem with a different set of elementary row operations, but the execution, if done correctly, should provide the same solution. So now we have x1 is equal to 5, x2 is equal to 2, and x3 is equal to -3, and we have a unique solution. Now, as I mentioned in the previous lecture, we found cases where we had free variables in the 2x2 systems, and we decided that we would use some arithmetic tricks to get rid of the fractions in the representations of the particular variables. And that was only the case because we ended up with a reduced matrix or a situation where we had coefficients other than 1. That is, we didn't move entirely to the reduced form. In some cases, I stopped before the reduced form in hopes of making the arithmetic a little bit simpler. But just remember, however you want to characterize your solutions when you have infinitely many or a free variable is completely up to you. If you're okay with the fractions, you can keep them, but you can always eliminate them and make your solutions look a little more tidy. Now, what I wanted to do was cover a situation where we have infinitely many solutions. That is, we actually end up with a row of zeros. Now, of course, when you think about this, maybe a few less operations, but then you have to navigate the parameter or the free variable. So notice the system here. Again, we have 3 equations and 3 unknowns. We have 2x1 minus 3x2 minus 13x3 equals 14. We have 3x1 minus 8x2 minus 30x3 equals 28. And then we have x1 plus 2x2 plus 4x3 equals 0. So the first thing we do is make the augmented matrix. Again, these equations are all in standard form. We have our variables on one side, we have our constants on the right-hand side. So that's the standard form to move all of the coefficients into the augmented matrix, which you see we've done here. Now, like we had in the previous problem, we do have a leading 1, but it is not in the position that we would like in order to create zeros. So because, again, we have the luxury of a 1 in the first column, we can simply do this. We can interchange row 3 and row 1. That is, move row 3 to the row 1 position and vice versa. So this will give us a new matrix where rows 1 and 3 have been reversed. So now, just like in the previous problem, when you do have the leading 1, making the zeros is very simple. So based upon row 2, we would multiply row 1 by -3, add it to row 2, and then, of course, based on this 2 here, we would multiply row 1 by -2 and add it to row 3. And then upon doing the arithmetic, ladies and gentlemen, we get our 2 zeros here, which is very convenient. Now, one thing you'll notice, which is exactly like the other problem, is we've got a -14 here, and we're thinking, okay, well, you know, the -14 and the -7 are very nice numbers when we want to create a zero. And you're thinking, I could go ahead and get a leading 1, but if you think about it, you can create a zero in a place that would be very, very simple. So notice, if we multiply row 3 by -2, that creates a 14. If we add it to that creates a 14 in row 3. And if we add row 3 to row 2, we get the 0 where we want it. Now, that doesn't take a whole lot of work, and it's easier because we didn't introduce any fractions. And so maybe later down the road, we could go ahead and reduce. But notice here, when you add the 14 to here, you get a 42. So you're thinking all of these are divisible by 14, so you could go ahead and create the leading 1. But I just want to show you that if you didn't see that, then you could go ahead and do this procedure and get the same result. So when we do the -2 times row 3 plus row 2, look, a row of zeros. So either way you want to do it, we get to our row of zeros even quicker. Okay, so now we're thinking, all right, well, that was an interesting way to do it. So at this point, we will use the definition part 1, which means to move the row of all zeros down to the 3rd row. But before we do that, and this is certainly possible, we're just going to go ahead and make row 3 even simpler. That is, we can just multiply by a negative 1/7 because each of these are actually what? Multiples of 7. So when you divide by -7 or multiply by -1/7, you get a row of 1, 3, and -2. Of course, the negative here with the 14 gives us the -2. And then we can go ahead and switch row 3 and row 2 and put the row of all zeros at the bottom of the matrix. So now when you look at this, number one, you know you're going to have a free variable, and number two, you're only going to have two leading ones. That is, there won't be a leading one in this position because the variable is free. Now, students often say, does it matter which variable we pick to be free? It does not. But based on this convention, it is much easier to allow the variable that's free to be the one that does not have the leading one. That is, x1 and x2 have their leading ones, and so we're going to go ahead and keep them as basic variables and use the variable to be free that does not have the leading one. That makes the convention a little bit easier to execute, and everyone does it the same way. So I would recommend keeping that type of convention when you apply the free variable. But now, of course, we need a unitary column here, so you can multiply row 2 by -2 and add it to row 1, and that gives you the 0 where you need it. And then the other two entries are easily obtained with the very simple arithmetic. Now, like I said before, we got all these nice ones here. We don't have to navigate any fractions or try to get rid of any like we did in our previous exercise. So now x3 is free. We just assign it the letter t, which is not required. But in many instances, the letter T or the letter S signifies a free variable, that is a parameter. And these are very useful letters for parameters, and they tend to be used in that capacity throughout mathematics, just something that has become commonplace. So now, if you look here and you just solve for x1, you transpose the -2, so you get x1 is 2t plus 4 because now x3 is just symbolized by the parameter or the letter t. And then, of course, x2 will give us the -3t minus 2 because you transpose the 3. So again, these are nice expressions, no fractions, and we can simply move to the solution set. X1 is 2t plus 4, x2 is -3t minus 2, and x3 here is just what? T. And then we denote t as being a real number in that it can take on any value you like. We're sticking to real numbers here, but we could use imaginary numbers too. It wouldn't matter, but these are basically solved in the real case, so we stay away from those. And then I just noted down here infinitely many solutions. So again, the key here is that the arithmetic is fairly simple. We got lots of practice with the arithmetic in the previous lecture, but what we want to do again in the process is just double and triple check the arithmetic to make sure we have accuracy. Simple mistakes are easy to make. We all make them. It's unfortunate, but we want to double check, triple check to make sure that we have good arithmetic. Now, what I said before is we can have situations where we have underdetermined systems. And then I'll let you look at problem 10, which is overdetermined, and you can see how there's no solution with that. I've kind of beaten that up with other examples. So I want to go on to an application. What I've done is I've provided a few additional problems from your homework just to give you more practice with some of the applications. Again, very straightforward, but what we find in many instances, ladies and gentlemen, is that we find underdetermined systems that if they do have solutions, then there will necessarily be infinitely many. So I thought this was a good example because many of the problems in your homework tend to be just like this. And use the other examples just to provide additional ideas about how you can work with the system of linear equations. In this particular example, we have a chemical manufacturer is going, and this is paraphrased, to lease 27 railroad tank cars with a combined carrying capacity of 576,000 gallons. Okay. And it says the tank cars with 3 different capacities are available. So you've got 3 different types of cars. You've got the 6,000 gallon capacity, you have the 12,000 gallon capacity, and the 24,000 gallon capacity. I don't, as I've said before, don't use the commas in the numbers because when you type these in your homework, you don't put in commas. I know that helps us, but it's kind of gets in the way and I just don't use them. So what the problem is probably fairly obvious to you. It would say how many of each car should be leased. How many of each car should be leased? That is, do we have 5 of the 6,000 gallon? Do we have 10 of the 12,000 gallon? And that's 15. So that's going to be a 5 and a 7. So that means we have 12 of the 24,000. Of course, that's just hypothetical. It's not correct. So we're thinking in this particular case, what do the hypotheses say about what possible solution scenarios would be available to us? So let's just write down the system with the very simple variables here. That is, X1 will be the number of 6,000 gallon cars, X2 will be the number of 12,000 gallon cars, and X3 will be the number of 24,000 gallon cars. So with that said, we can go to the first line and know that the sum of the variables must be 27. And since we know the combined carrying capacity of all 27 cars, we can simply multiply each of the variables by their corresponding capacities and set that equal to 576,000. That's it. That's all we know about this leasing operation. But it's more than enough to come up with a solution if there is one. So we have what, as I said before, an underdetermined solution or a system. We have what? 3 variables and only 2 equations. So as I've said before, and you can do this piecemeal, what's the main purpose or the motivating factor when we do the Gauss-Jordan process? The first thing we noticed, even before we started using the Gauss-Jordan process, is that we would always eliminate common factors, and that is critical. When you work with friends or colleagues with arithmetic, the goal should be to reduce the numbers to smaller size. Smaller magnitude always will engender a more simple solution. So what we notice here is that each of these coefficients, the author was very good to us, are all divisible by 6,000. Now you can break this up into 2 pieces, divide everything by 1,000, and then hit everything with a 6. That's your choice. But notice if we divide 6,000 by 6,000, we get a 1. If we divide 12,000 by 6,000, we get a 2. If we divide 24,000 by 6,000, we get a 4. And then, of course, if you think about this, the zeros absorb, and you just divide 576 by 6, and you just get 96. So you're thinking, wow, that is a huge reduction. And so now you're thinking, this will not be difficult to solve. We have only 2 equations, and look at the leading one that we already have. So again, we multiply by a very useful constant here to reduce the size. That is critical, ladies and gentlemen. The smaller numbers are always easier. And so now we've got a leading one, so we need a zero. So we simply multiply row one by -1 and add it to row two. Very simple arithmetic. We get our zero, or our unitary column, and then we have a 1, a 3, and a 69. And so there's not much left to do to get reduced. Of course, we can make a zero here, and this becomes a leading one. So now what we want to do is just work back up. So we multiply row two by -1 and add it to row one to work back up to create a zero. And so now we have the zero here, and then we end up with a -2 and a -42 here. Again, we got used to the basic arithmetic that we need to be able to do, but the impetus behind that is the creation of the zeros, because that makes the solution obvious to us. So now when we look at this, ladies and gentlemen, this is indeed reduced. We have the staircase pattern of the leading ones. We have unitary columns for leading ones. We have no row of zeros. So now we can see that the x3 will be the free variable. So we just say x3 is free. And then to use the terminology I stated before, we'll say x1 and x2 are basic. We'll actually use that when we discuss the simplex method. So now, of course, we'll use our favorite letter t to represent the variable, t a real number, so x3 is set equal to t. And so now we can solve. Notice here, if we transpose the -2, x1 will be 2t minus 42. And if we transpose the 3, x2, in this case, will be 69 minus 3t. Now, with the applications, of course, infinitely many doesn't always ring true, because we need the values for x1, x2, and x3 to be non-negative. They certainly couldn't have negative values. That would make no reasonable sense for the problem. So when we think about this, this just means for x1 to be positive, that what do we have? T minus 21 is greater than or equal to 0, or t is greater than or equal to 21. Of course, t must be greater than or equal to 0 just by the given. And then, of course, for 23 minus t to be greater than or equal to 0, that would mean t would have to be less than or equal to 23. So all of these are appended by and. They all have to be true. So when we look at this, we see that this kind of gives us where we need to be, but we know that based on all of these being true means that, okay, we must be less than or equal to 23, but greater than or equal to 21, and that will take care of the greater than or equal to 0. So now we see that there are actually only 3 values of t that make sense for this problem, but that's actually good. If this is a production process, then now they can decide. It's like, okay, well, we've got 3 options here, and then those options can be chosen based on other circumstances that may have to do with price and profitability when it comes to this process. So now what you see is the values of t equal to 21, 22, and 23 will give us values for the variables that make sense for this problem. So at least as an introduction to the Gauss-Jordan elimination process, we see that the reduced matrix allows us to characterize the solution very efficiently. And depending on the size of the system, we don't have to worry about carrying around variables. Our goal is always reduced matrix. And then, of course, with that, if we get 0 equals 3 somewhere, then we can stop. I always said before, once you find something like that, moving on to a reduced matrix may very well be a waste of time. Well, it's not very well be, it is. If you've got a contradiction, then there's nothing you can do to fix that. So maybe you might look at that and say, well, I don't want to go on to the reduced matrix unless the professor just said, please do that anyway. So notice, again, what we're going to see as we continue with this process is that since we have positions in the matrix for every entry, this is something that we call an array in computer science. And so this process can be coded, and then you can have a computer crunch the numbers. You enter all the data, and the computer can crunch the numbers to give you a very valuable and correct solution. So again, think about what you learned in your earlier algebra classes and basically see how this is indeed an improvement over the original method that we had. So again, as we continue, the next topic will be basically matrix theory, where it involves using arithmetic to combine matrices. And then we will morph that into some other properties and other operations, and then move that eventually into the simplex method. So I hope that this has been able, or what I've said today has been able to actually introduce the idea of reduced matrix and how it can actually help you in solving systems of linear equations. Okay, we're done. Have a good day.